Hello and welcome to this video, which is an introduction to volumes of revolution. So this section here is taken from the textbook and it just summarizes the idea that you've already met integration to work out the area under a curve, okay, by summing up lots of little rectangles. But if you imagine rotating those rectangles around the x-axis or the y-axis, you trace out lots of cylinders, so you get a slightly different formula based on pi r squared h. So here is the formula for the volume of revolution when a shape is rotated around the x-axis. V equals pi times the integral of y squared dx. And if instead you were rotating around the y-axis, the formula would be V equals pi times the integral of x squared dy. As a little thought experiment, just imagine rotating each of these areas around the x-axis. The one on the left would trace out a cylinder. The one in the middle would trace out a hemisphere. And of course, if you took a semicircle and rotated that, you could trace out a whole sphere. And the one on the right will trace out a cone. So we're going to look at some examples from the handout. Firstly, find the volume when the area enclosed by the curve y equals 5x squared minus 6, the x-axis, and the lines x equals 2 and x equals 7 is rotated through 360 degrees about the x-axis. So using pi times the integral of y squared dx, our y equals 5x squared minus 6, and we're doing it between the limits of 2 and 7. And because it's about the x-axis, we're using y squared dx. So substituting 5x squared minus 6 for y, we need to square it first. Then we need to integrate it, which gives us pi times 5x to the 5 minus 20x cubed plus 36x. And then we're just substituting 7 and 2 as we did before for area. And the answer is 77,355 pi. In this question, we're given the curve. And again, we're going around the x-axis, but we don't know exactly what it looks like. We haven't been told the limits of integration. So you can see I've drawn a sketch. It's a negative cubic. It meets the x-axis at 0 and crosses at 4. So we're integrating between 0 and 4. Again, we're squaring y. So the first thing I've done is to multiply out the brackets and then square it. Okay, and then I've integrated it. And when I substitute in 4 and 0, I get 16,384 over 105 pi. Okay, again in this second question, we're going around the x-axis. We're doing it for a straight line. So y equals x plus 3. We square the straight line, we integrate it. And then we substitute in 3 and 1, and we get 152 thirds of pi. Just for information, we could, of course, actually work this out without using calculus because it's a frustum. It's the area between 1 and 3 rotated on the diagram. So what we can actually do is imagine that we've got a large cone take away a small cone. So by extending the straight line, we can see that it crosses the x-axis at -3, which means that the height as well as the radius of the large cone would be 6, and the radius and the height of the small cone would be 4. So you can see I've used the formula for the cone and I've got the same answer of 152 thirds of pi. Here's a very basic example on trigonometry where y equals sec x. Again, we're going around the x-axis between 0 and pi over 4. Again, we need to square y, so that's sec squared x, which you should already know has an integral of tan x, but it's also there to remind you. And then we're substituting pi over 4 and 0 into there, which gives us 1 and 0. So that's 1 take 0, which is 1, multiplied by the pi on the front, and the answer is pi. This question is about rotation around the y-axis, which, to be fair, is the same as many exam questions where often you're forming bottles or vases or chess pieces. So the y-axis is a very common axis to rotate around. Anyway, we need to use this formula, adapted, v equals pi times the integral of x squared dy. But notice that we've been given y equals 2x plus 3, and we need to make x the subject. So if we take away 3 and divide by 2, then x is equal to y minus 3 over 2. And then we're going to square that and integrate, and it's between the numbers 3 and 9 because they're the y values that we're using. So as you can see from the solution, we square it, we integrate it, we substitute the numbers in, and the final answer is 18 pi. So for our final example, we're looking at a composite shape. We have a cubic graph of x cubed plus 2 and a straight line with a negative gradient, and also the two axes bounding our area. it's going around the x-axis. So the first thing I've done is to draw a graph to show us the shape. Okay, and if we imagine drawing a vertical line down from where the cubic and the straight line intersect, that divides the area into two shapes, one of which we can evaluate by integration, and one of which will give us a cone when we rotate. So the first thing I've done is to put x cubed plus 2 equal to 5 minus 2x to find that intersection point, which turns out to be 1, 3. So that means that x is 1. So when we're integrating using pi integral of y squared dx, we're integrating between 0 and 1 for our cubic curve. That gives us 36 pi over 7. And then for our cone, the radius is 3, because that's the value of 3 that we got when we solved the equation. The height is 3 over 2, because it goes from 1 to 5 over 2. The volume of the cone itself is 9 over 2 pi, and when we add them together, we get 135 pi over 14 as requested. Thank you for watching.